Thank you, Akil, for that warm welcome. Hope everyone's having a great GTC. This has so far been, I think, the best one ever. Lots of excitement. I see a lot of smiles. I think the future is looking pretty bright for us. We're here to talk about physical AI. There's still some confusion as to what physical AI is. Can we go back one slide? I don't know why it skipped to this one. There we go. There's been a lot of confusion as to what it is. So maybe we can spend a minute or so explaining it from NVIDIA's perspective. I think it's no secret now, AI is a pretty powerful force, big game changer for humanity in general. I think we're seeing the benefits of AI in productivity, in the knowledge space, in the information space. But one thing that's very clear, looking at what humans value, as measured by GDP, as measured by our markets, is that a small fraction of our economies are actually about knowledge, about information technology. It's only about a few $1 trillion. Very big number, but dwarfed by the size of all the other industries. If you take all the other industries, which aren't about ones and zeros, they're about atoms, these form more than $100 trillion of value that we create. This is industries such as agriculture, transportation, construction, life sciences, manufacturing, and so on. You take all of these together, and this is where value is truly created for humans, for all of us. Unfortunately, the great tailwind that has been computing over the last few decades has largely not touched these industries. Mostly, the computing industry has benefited in the information space, the knowledge space, for knowledge workers, giving us orders of magnitude more productivity in that space, but hasn't helped us much inside these spaces. For the first time, because we have this new AI technology, this ability to train computers to learn about the world, learn about things based on information we give it, we now have the capability of applying computing to apply this great gift we have of exponential growth in computing capabilities to the world of atoms, to all of these industries. And the way that meets is through robotics. We interface computers and computing with the physical world to manipulate atoms by giving these computers bodies, by giving them physical representation. And so physical AI is basically just that. It's all of the AI, the brains that we are going to create to power these robots. This clicker's not advancing. Can we advance one slide, please? The way it works is, the way any robot really works, is by doing three things continuously in a loop. We first ingest the world through sensors. We take that world through the sensors, convert it into tokens that we then feed into an AI. And the AI can understand the world and start making decisions about plan and decisions as to how to actually act within the world. Converting those input tokens into action tokens that are then sent to the body of the robot to go act upon the world. This thing is done in a loop because as the robot acts upon the world, you then need to see what happened, perceive it, and make new decisions and continue doing this forever and ever. The way we look at robotics and robotic systems, there's many species of robots out there, and actually the class of things that are robots, from our perspective, is probably much wider than what most people think. The first type of robot that we've been working on for the past 10 years or so is autonomous vehicles, making cars that can drive themselves. That's a very important robot, and it's one that is now scaling. We're seeing it deployed out into the real world. Infrastructure and spaces can actually be robots. Buildings, cities, construction sites, farms, all of these sorts of spaces, if you instrument them with sensors, they can perceive themselves. The spaces can perceive themselves backed by AIs that can make decisions upon how to act upon that space. And they can deploy other robots or control systems inside those spaces to react accordingly. Of course, there's the robots. Those are the things we normally think of as robots, like humanoids or AMRs and manipulator arms. And then there's a special kind of robot that's starting to emerge, which are healthcare robots, both robots that assist healthcare workers and robots that actually perform surgery. These are a special class because they have very, very different constraints than the general kinds of robots. We work on all of them. To build these robots and robotic systems, you need 3 different computers. The first computer that you need is the computer to actually train or build the brain of the robot. This is largely what most of you are probably here for. This is what NVIDIA has been doing for the past decade or so. And after the ChatGPT moment, everybody realized this is a pretty important thing. We build these DGX computers and provide them everywhere. So these are the computers in the cloud generally, where we do massive amounts of computing to take all of this data and produce a brain. But in addition to that, you need the computer that's inside the robot, the one that's doing the inferencing, that takes the brain and actually executes and performs in the real world. We build those with our Jetson and IGX systems, as well as the software stack on top of that, and many of the algorithms that you need to operate it properly. The lesser-known computer by most people for robotics is the simulation computer, or what we sometimes call the Omniverse computer. This computer is essential to build robotic systems. In order to train a robot brain, you need to provide it with information about the physical world so it can understand the physical world. We can't get all the information we need from the actual physical world. It's too expensive, costly, or dangerous to do that. So instead, what we do is we bring the physical world into the computer. We run simulations. Those simulations generate the data that we need in order to produce the brains through the AI computer. We also use that same simulation computer to test and validate the robot brains, to test the robots before we actually deploy them into the real world. We build all 3. We've had industrial robotic systems for decades now, but largely this ecosystem has been kind of small and niche. It's been very hard to build robots and deploy them at scale, and so it hasn't really scaled up. But with the invention of modern AI, we now have a path to building intelligent robots that are easy to program and deploy. And as a result, what we're seeing is the formation of a much larger industry, a much larger ecosystem of robotics. And you can see there's many different companies participating here. This by no means is a comprehensive set of all of them, just what we could fit on one slide. But we have companies that have been working in the space for many decades, and many new AI native super startups within the space, doing a range of things, from building the actual robots, the physical robot bodies themselves, to the brains, to the systems to orchestrate and deploy them. It's really exciting to see. We're seeing the formation of all of this, and underpinning all of that is computing technology, these 3 computers that I just spoke about. And NVIDIA is part of all of that. Basically, every robotics company that exists today is using NVIDIA in one form or another, making NVIDIA the largest robotics company in the world without actually building robots. We don't do that. We have to work with the rest of the ecosystem to actually bring these robots into the world. We started working on robotics and physical AI over 10 years ago. We started with the first type of robot, the transportation robot, autonomous vehicle, and it was a long road. When we started, deep learning was in its nascency. We didn't have the capabilities to train really general purpose AIs and models. And the computers that we produced at the time, although they were very powerful, I believe that first one, Parker, was 1 TOPS, 1 trillion tensor operations per second. We didn't have the capabilities to really make a very intelligent driver brain quite yet. But over the years, we figured it out, and with the creation of the transformer technologies and end-to-end models that we helped pioneer, in the past few years, we've had a breakthrough. We now have reasoning models, much like the AIs that we use for ChatGPT and Claude, but working in the physical world to reason about what the car experiences in the world and deal with situations that it has never experienced in its training data. This is a huge unlock, and now we're seeing this essentially be the reason why autonomous vehicles are going out at scale. And luckily, we've done all of that work in this particular space with these kinds of robots, so we don't have to go through the same journey again with every other kind of robot. We can just take all of these learnings and go straight to the right answer with every robot to come. Within the autonomous vehicle robotics space, we're paving the way to L4 autonomy. At CES, we released an open source model called Alpamayo from our Alpamayo family. It's an end-to-end driving model that reasons. We are releasing the Alpamayo 1.5 model, topping leaderboards, and the number of downloads is crazy. I encourage anybody in this space to go take it, or even if you're just curious, go play with it. Along with the models, we also open up everything else necessary in order to build such models. So we are open sourcing and opening up, and have opened up actual real driving clips that we captured from our fleet of cars in the real world. We have also open sourced frameworks, including Omniverse, NeRec SDK, which is a library to capture the physical world and reconstruct it for simulation for this purpose. And we also have blueprints that you can use as the reference architecture to start building your self-driving cars. Factories themselves are now robotic systems. Essentially, the robots I was talking about, the different classifications, if you take the combination of all of those, you can combine them all together to create a system, a factory, that's essentially a robot itself. So a factory is a space that can have many sensors, cameras, and other types of sensors to watch itself. But within the factory, you have many types of robots. You have transportation robots like AMRs and manipulator arms, and now we're starting to see humanoid robots show up in them. So the combination of all of these as one system makes the whole factory a robot. There are 2 types of factories that we are building. First is the kind that we've always known. When you think of factories, they're factories that produce physical goods, all the products that we consume. At NVIDIA, we make great use of these to build the computers that are being used to produce AI. But there's a new kind of factory that's driving the largest infrastructure build-out humankind has ever known, and these are intelligence factories, factories that produce intelligence, that produce tokens. We are using simulation, and we're using robotics, robotic systems to develop both of these at rapid scale. These factories, the modern factories that we're building, are so complex, it's basically impossible to build them in time, to build them at cost, to have them operate correctly without simulating them first. We have to design them in a computer, and we have to simulate them and make sure that they work correctly before we deploy them out into the real world. Even once you deploy them, you want to make sure that all of the robots that you're going to place inside these factories, they all perform correctly. You want to commission them and make sure the whole system works correctly. The only way to ensure that you have all your software and the robot brains done correctly is to simulate it beforehand. So all factories are born in simulation. Here we see many examples from our partners who are using simulation and providing simulation built on top of our technologies to build factories. From PepsiCo to who is using it for their supply chains, and Crohn's, who is building these systems to do bottling of these types of things. SK Hynix, very important for us here in the AI ecosystem, and speaking on the panel with me later, optimizing their factories to produce the memories that we need for AI. We have, as you all know, an extreme problem with the availability of memory, so it's really important that we do this quickly and bring up new fabs. So building robotic factories that can learn and optimize themselves is critical, and they're doing that. Then we have GXO and Kion, along with their partners and our partners, Accenture and Siemens, building robotic warehouses for supply chain and logistics. All right. I spoke a little bit about these AI factories. I know Jensen spoke a lot about it, but it's worth repeating here. AI factories are the new industrial infrastructure. Every company needs this moving into the future. It's impossible to imagine that your company does not need intelligence. Anything that we are doing, any task worth doing, is amplified and benefits from more intelligence. For the first time, we have the ability to manufacture intelligence. The way we do this is by essentially taking the raw inputs, which is energy, and we take our raw information and push it through these massive machines that produce tokens, which are our units of intelligence that are very, very valuable, far more valuable than the inputs. Just like traditional factories, these AI factories have to operate at peak efficiency. We are fundamentally limited by the inputs we can put in them, the energy. That is our fundamental bottleneck. Anything we can do to get more tokens for every unit of energy is essentially revenue for every company. This is what we're working on here. This is what GTC is all about. It's about building the infrastructure for this new economy, for this new world where everything is powered by intelligence, powered by these factories that are limited by the amount of energy coming in. So we need to maximize uptime, maximize the quality of the tokens that come out, and maximize the number of tokens per watt. To do this, we have to employ the same technologies that we're using these machines to create, which is AI and simulation. In order to do this, we can't do it alone, of course. This requires a whole ecosystem, basically everybody working together to bring their piece of the puzzle. We need to simulate the combination of every aspect of these AI factories, from the mechanicals, thermals, the network load and how that affects the heat distribution throughout the systems, the grid, the substations that transform power from the grid into one that the factory itself can consume. Every 1% of optimization you can do translates into billions and billions of dollars for these AI factories that we're rolling out that cost us in the trillions. To do that, everybody has to work together, and so we are leading in the whole effort to build out this infrastructure, and as a result, it is our burden to go organize everybody else to come together to work on their different parts, and we do this by providing reference architectures, combining all of the great tools from companies such as Cadence, Dassault Systèmes, Siemens, PTC, Schneider Electric, and everyone all come together to build a reference architecture, to build out a simulation framework for every aspect of these AI factories we can then use to do these massive optimizations with extreme co-design across every aspect of the AI factories. Now, a big topic at the keynote yesterday, and I think just in general, everybody's hearing about these, is these crazy agents that have just come out of nowhere. For the past few months, many in the technology and software community have been going crazy with these coding agents. And in just the past 2 months or so, OpenClaw came out of nowhere. And as we saw in the keynote yesterday and in this chart over here, within a month or two, it overtook basically every other major open source project as the most widely downloaded and starred project on GitHub. The reason for that is that this change from using AI as a tool that augments a human to AI becoming something that is autonomous, that can do things for a human on its own for a long period of time, is not just an incremental change. This is a binary change in how we are going to work, and a binary change in a step function change in the capabilities we now have. For the first time, we have the ability to manufacture knowledge workers. These agents you can think of as robots. They're robots that work autonomously for a long period of time, but they work using computers, much like our laborers who work in the knowledge economy use computers to do their work. These agents have agency. They can go do things. They can go use tools. They can also organize other agents to do things. So we've realized exactly what this means, that this is a fundamental disruption to everything we've known about engineering software systems and computing systems. Within the Omniverse team, we realized it pretty early, like a month ago, at the same time some others have, and decided that from now on, what we need to do in order to really supercharge physical AI is make it easy for these agents to use all of the software and all of the tools that we have built to go build the solutions and the tools and the simulations, the particular softwares that every one of our partners and customers needs to fulfill their needs and solve their problems. We are already on the road to decomposing Omniverse into these smaller library modules that could be integrated directly into existing softwares. It turns out these same modules that we were building for that purpose are perfect for agents, for coding agents to take and to go integrate themselves. We have already released a few of these, and there's many more to come. We have OVRTX, which is essentially the Omniverse rendering, the Omniverse renderer combined with USD, presented as a simple library. We have OVPhysX, which is our physics components, OV Storage, which connects your native storage backends into the USD ecosystem. And then we've also released SimReady. It's a set of libraries, tools, and validation pipelines so that you can ensure that the assets you create are natively work inside a USD workflow with all of the simulation properties and everything necessary to simulate them correctly for the purposes of robotics. All of these are now available, and very quickly we'll be releasing more and more, so keep an eye out for them. We're very proud to be working with all of our partners to integrate our technologies and these particular libraries into their offerings. Yes, I was just mentioning the SimReady libraries. This is a very critical aspect of what we do. Even if you have a great simulator, you have a great simulation stack, if you don't have representations of the things that you need to simulate especially complex things like our factories and warehouses, if you don't have every component of the things in there in a form that is easy to bring together and simulate, then it doesn't really matter. We've been pushing for years to bring standardization across all of the tools, across all of the pipelines, across all of the manufacturers of the things that we build in the physical world, to produce these assets that could just drop into a simulation environment and just work. We're getting closer and closer to this. We just announced that we release an SDK that will help anyone that is trying to produce these simulation-ready assets validate and evaluate their assets, make sure they conform to the standard. And so I welcome all of you to use that and also to join us in advancing the standards as we build them. These agents that I was just talking about, they're already doing all these amazing things for us, but from the perspective of digital twins, from the perspective of robotics and simulating worlds for robotics, these are particularly not just useful, they're transformative to how we're going to work. The biggest limitation that we've had, the biggest bottleneck in terms of simulation, has always been the fact that we have a very limited number of people who understand simulation well enough to build worlds that can be simulated, that can operate these simulators to give us answers. We're bottlenecked by the number of people who have these skills. If you go to any large company that uses simulation to design their products or to design their factories, there's generally a very small team of people that have this kind of expertise. And so we just end up not using simulation where we should. We'd like to use simulation to ask what-if questions about your product, about possible ways in which you can change your product to make it more optimal, to make it more delightful. But we just don't ask those questions because it would require so much expertise to go build that, to build the simulation itself and operate it. These agents, these claws that we are now experiencing are perfect for this problem. We can take these agents, we can start building specialized agents that know how to use 3D tools, that know how to build things inside the 3D world, that know how to take our simulators and tune them and operate the simulators so that we can run these simulations efficiently and simulations that give us correct answers. And we can then use these same agents to evaluate the results of the simulations and test those results against the real world. All of this stuff has been inaccessible to most companies. Most people don't have simulation expertise. But for the first time, we can actually manufacture the expertise to go do that. And that's happening as we speak. It's the most exciting thing I've seen in my whole career, in my lifetime. And so I urge all of you to go take a look at that. And we're starting to see some of the beginnings of it. Here, I'd like to call out some work we've been doing with PTC. They've integrated the Omniverse libraries into their Windchill PLC or PLM system. We use Windchill in many of PTC's tools to help design to design our computers, to design our hardware, and put it out there. But we also have been working with the Onshape team at PTC, who has been pretty important in the nascent robotics community, in this AI native robotics community, for designing the physical things inside the robot world, the robot bodies. They have integrated parts of Omniverse to make it seamless to produce robots inside Onshape, to produce physical things inside Onshape that export immediately as sim-ready assets into Omniverse-based simulators like Isaac Sim, so that you can have a very seamless transition there and have a very high-frequency loop so that the designers can test what they are designing as they're simulating it. So it's really great. Take a look at that. We also have, we had a little bit of this inside Jensen's keynote. We've connected up Onshape along with one of these Claw agents and found that almost immediately it could start using the simulation tools along with the design tools in Onshape to redesign something like a gripper to more accurately and with higher performance be able to perform its task. Be on the lookout for that. It's very exciting. We also have this other class of robots, the infrastructure robots, ones that watch spaces and look out for issues and problems and things that are occurring outside in the real world. We have Siemens Energy integrating many of our libraries, including Metropolis and Cosmos, along with Omniverse to inspect power lines. We have FogSphere, who creates the same kind of robotic infrastructure for inspecting construction sites and making sure that people are safe and we have minimal incidents, and when we do, the response times are great. We have Hitachi also doing the same kind of robotic systems for looking at our infrastructure, physical infrastructure like transportation and roads and so on. And Linker Vision, where here in this city of San Jose, they've essentially turned the whole city of San Jose into a kind of robot that monitors itself and optimizes the city processes. At GTC, we are announcing some new NVIDIA Cosmos models. For those of you that don't know what that is, Cosmos is our World Foundation model. It's best in class for true physical AI. These World Foundation models are the analog of LLMs. What LLMs are to text, to language, World Foundation models are to the physical world, to the laws of physics. We use Cosmos to do many things. We use it to understand the world and reason about it. It is at the core of what we built into our robotic brains. We use Cosmos to predict the future. So given a moment in time, an instant, a video frame, it can predict what should come next, but be physically plausible. And so we've released Cosmos now. I think it's been about a year and a half. It's topped leaderboards and downloads, but we're not sitting still. We have Cosmos 2.5 out right now, and Cosmos 3 is coming soon, where we are fusing more aspects of Cosmos into a single model, the prediction and the understanding aspect of it. Along with Cosmos, we don't just release the models in open weights, but just like Alpamayo in the AV space, we provide the data we use to actually train Cosmos, so you can go build your own World Foundation models using the same data. We also provide all of the frameworks we used to build and use Cosmos. And we provide blueprints as a reference architecture for how you can use Cosmos in your applications. There's a new class of physical AI startups and companies that has arisen. Basically, in the past few years, since ChatGPT came out and the whole world understood for the first time that this AI stuff we're talking about actually is something very different. For the first time, we have the general capability of interfacing with a computer like it's something like a person. You can have a general intelligence and do things generally. Once we understood that, many people around the world understood that application into the physical world, into robotics, was now possible. And so we're seeing the creation of a whole ecosystem in front of our eyes, and with many new companies and entrants that are coming in. It's very, very exciting. There's within this ecosystem, we have humanoid robotic makers like Figure, Agility, and 1X. But we also have many companies that don't actually build any physical robots, ones that just build brains, an equally important part of this, like physical intelligence, skilled AI, Mistral, and so on. Many are forming every day. Keep an eye out for all of them. Hopefully, probably many of you are working at some of these. In order to build a robot, you need a full stack of capabilities to make it possible. The building of a robot and a robotic system, as important as the physical body is, it's not sufficient. It really starts from data. In order to build the brain for the robot, you have to actually have enough data about the things that it's going to do and about the things that it might see in the future that it hasn't already experienced. So to do that, we provide many simulation technologies and tools. We have Isaac Lab, which is our reinforcement learning framework to train robots, give them millions and millions of hours of life experience before putting them out there. And once you build these brains and these policies, you can then deploy them out into the actual robot, which has a computer inside the robot. We have multiple computers, depending on your particular use case. You can choose whichever one is more appropriate. We have Jetson Thor, which is the de facto standard for all advanced robotics today. But we also recently released IGX Thor, which is a industrial class computer built on the same architecture, the same GPU. But if you have industrial grade uses with industrial grade safety, it's more appropriate for that. And we also provide an open source set of models and frameworks for building a robot brain. We call it Groot. And so here you can see some examples of our partners with Agility, 1X, and Hexagon using all the pieces of this. And of course, Cosmos is also a critical part of this. It's what we use to take the simulation data that we produce using classical simulation and multiply it by orders of magnitude into more data. Something that's really great to see that's happening right now is the robotics industry, as it's existed in the last 2, 3, 4 decades or so, is now starting to combine and work with the new robotics entrants, the new robotics industry that's forming. We have these great companies like ABB, Fanuc, and KUKA who have been bringing robots to industry, building robots that can work 24/7 in these crazy conditions with extreme reliability, doing the same tasks over and over again without failing. They know how to build great robot bodies. And all of that knowledge is essentially they're contained within these companies. At GTC, at this GTC, we announced that ABB, I believe, ABB and UR Robotics, Teradyne, are working with Skilled AI, one of the robot brain makers that's also being featured here, to bring their robot brain intelligence to their existing industrial robots. This is really amazing, and I think this is the trend that we're going to see accelerate, where the problem of robotics being too large for any one company to solve, we're going to see an ecosystem form where all of the different players focus on their expertise and work together to build something much greater than any one company can create. Another big change that has occurred, and probably the single most important reason for why we're seeing autonomous vehicles take off with level 4 autonomy and what we were able to do with Alpamayo, is that the traditional moats, quote unquote, that existed with those that have large amounts of data about a problem domain has essentially disappeared. The thinking was that in order for you to deploy a large robotic system, you need to have a large install base of robots to go capture information about the world. For example, a large number of cars that have sensors to capture information about all the roads. And that data would be a moat that would not allow other entrants into the industry. Well, it turns out that the way we were training our AIs in the past is actually not the best way to do it. If you have to gather data about every possible thing that might happen in the real world, you're always going to fail. We can't gather enough information. And if you think about it for a second, humans don't actually have to see every possible situation before they can go out into the world and do things. We teach 16-year-olds over here in the US how to drive with very little information. It's maybe not a great idea, but we do it. And eventually they figure out how to get better at it. And so we've done where we got to with these advanced reasoning models is a place where we can train up our robotic brains in the same way we train humans and other animals. So here you see what the overall pipeline kind of looks like. We first start by gathering all the information we can about the world at internet scale. We get all of the videos and everything we can find about the world, and we create a pre-trained model that has general information about how the world works. We then take data that's generated through simulation, both classical and neural simulation, and we post-train these models to create a more specific intelligence, one that's more of a specialist about what to do in the world. Instead of just knowing generally how the world works, it might know how to do a particular task in a particular environment, like work inside a factory on a factory line. Once you have that, you can then use that model to go train and evaluate inside simulation and see how well it works. And what you learn from there about where it works and where it fails feeds back into the post-training data loop. So you can augment your post-training data with more data to compensate for this. And you go round and around in a loop like this. But the key to all of this is that for the first time, we have the ability to pretty much automate all of that so there doesn't have to be a human inside any part of this loop. And we don't have to go capture this data from outside, from the real world. We can generate this data, and we can keep improving the intelligence simply by providing more compute. So today, this data moat has now disappeared, and compute is the new data. But what that does mean is that we're going to need more and more compute, which is what we're starting to see. This is why Jensen announced that our previous estimate from a few months ago of $500 billion to $1 trillion in orders has happened. All right. I'm going to rush through a few of these slides, if you guys don't mind. I'm getting some signals over here from Lexi that I've probably been talking a little too much. We have the physical AI data factory blueprint that we announced. This is a key part of turning compute into data. Look out for that. This is a reference architecture for building this up with data generation, augmentation, and evaluation. We have it available through some of our partners with Microsoft Azure and Nebius, and already we are seeing many of our robotics and AI startups and companies using it. We are also announcing new versions of Isaac Sim, Isaac Lab, Groot, models and libraries. Take a look at all of them. These are topping leaderboards and charts. All of it is out there. It's freely available. It's open. We want the world to go take this, build on it, make it your own, use what works for you, use the pieces that work for you, build the pieces that don't work for you yourself, and combine it all together into a system that's perfect for what you need. And back to the ecosystem, the ecosystem I showed at the beginning of this is essentially all building on the 3 computers. These are just, again, a small number of companies that we are working with, that we highlighting here. You can see all of them at GTC. The slides talked about the industrial age, the robotics companies meeting the AI natives. Next slide. All right. And so the 3 big takeaways I would like all of you to walk away with is this new agentic era that we are in now is the big unlock for building physical AI. All of you should be becoming expert in this. Go take a look at it. Don't wait to start using these coding agents, to start using these claws. Immediately start learning about it and see where you can apply it into your pipelines, because this is going to be a multiplier that gives you orders of magnitude. Compute is data. So in order to enter this robotics game, you no longer need to go gather all of the data that you need from the real world, which is costly and time-consuming. You can turn compute into your data. And take a look at the robotics ecosystem that's being built around us, with NVIDIA powering and underpinning pretty much all of it. At 11 o'clock, I'm not sure what the time is, in a few short minutes, we're going to have a great panel with many of our great partners who I highlighted earlier. So please stay here for the panel. And wasn't there another slide with the other sessions? Okay. All right, thank you.